angular momentum. The equivalent concept that we have introduced for linear motion is the linear momentum. P equals mv. By comparing the two equations, you can easily relate the linear momentum to the angular momentum. You can relate the mass, which is the linear inertia, to the moment of inertia. And finally, you can relate the angular velocity to the linear velocity. And that's what the angular momentum is, and it is indeed a vector quantity. Recently, we have introduced Newton's second law for rotational motion, which is the sum of the torques equal I alpha. Alpha is known to be the change of angular velocity over the change of time. Making simple substitutions, the sum of the torques, that's known as the net torque, equals I times delta omega over delta t. I would like you to focus on the quantity here, I times delta omega, this quantity. This is the change in angular momentum. We have introduced the angular momentum to equal what? I times omega, which means now what? The delta L is I times delta omega. Therefore, the final expression that I am going to write down here is the net torque equals delta L, the change in angular momentum, over the change of time. I have been able to express the net torque in terms of the change in angular momentum for a very important reason, which is the condition that the law of conservation of angular momentum requires. What does it mean, conservation of angular momentum? It means that the angular momentum initial has to equal the angular momentum final. That means the delta L has to be 0. I would like you now to focus on the following expression right here. If the delta L is going to be 0, the condition is the net torque has to be 0. If delta L is to be 0, what is the condition? The condition is the net torque has to equal 0. We have learned about 3 conservation laws so far. Conservation of energy. Let me remind you of the conditions for those to be true. Conservation of energy means the work done by non-conservative forces needs to be 0. Conservation of linear momentum means the net force needs to be 0. And now the condition for the angular momentum to be conserved is the net torque needs to be 0. Here is a very good example that we usually display for the students in class. A student sits on a rotating stool holding 2 weights. We spin the student and we let the stool and the student spin by themselves. While the stool is spinning, the student pulls his arms in from the initial position, which is this one here, this is initial right here, to a final, which is here. The student initially is holding the weights with his arms wide open. When he brings the weights closer to his body, we notice that his angular velocity increases. We need to explain this. The action that was done by the student is an internal torque. He was moving his arms in and out. That's done internally. So that's not part of the net torque that comes from external forces. by bringing the weights closer to his main axis, closer to the body, he is reducing the moment of inertia, because we said early on that the moment of inertia depends upon the mass and where the mass is located. The closer it is to the axis of rotation, the smaller the I. The farther away the mass from the axis of rotation, the larger the I is going to be. So by bringing his arm in this final position here, the student has reduced the moment of inertia. Let me write down this one. I final is less than I initial in this case. But what do we know? We know that the I initial, omega initial, equals I final, omega final. If I final is reduced and the product I times omega got to remain constant, do you know what that means? It means the omega final has to be larger than the omega initial. And that's the explanation why the student starts spinning faster when he brings the arms in with the weights.